Do you know the electromagnetic spectra of X-ray, where it lies? What is the wavelength range of typical visible spectrum? Anyone? Electromagnetic spectrum, gamma rays, X-rays, UV, vacuum ultraviolet, far ultraviolet, mid ultraviolet, near ultraviolet. We call it as C, UVC, UVB, UVA. Near ultraviolet means near visible range. So then, so wavelength actually visible range is 400 to 700 or 750 nanometers, we say. Right? What is the wavelength of visible range? 400 to 750 nanometers. So 400 nanometer to 700. Okay, nanometer. What we call usually they are visible. Okay, below 400 nanometers and above 700 nanometers. We call it as above red it is. So we call it as infrared, right? And below 400 it is below violet. What is that? Ultraviolet. Do you know this electromagnetic spectrum? Anyone? Yes? Are you listening to me? Are you listening to me? Anyone?
Yes, sir.
Yes, sir.
So below 400 nanometer, it is called ultraviolet, right? Ultraviolet range. So ultraviolet is usually 200 nanometer to 400 nanometer, right? Right. So below 200 nanometer, we call it as vacuum ultraviolet. Then below that, we have X-rays. 0.154 nanometers is X-ray of copper K alpha radiation that we use commonly for XRD analysis. X-ray diffraction. X-ray diffraction is an effective method for determining the crystal structure of materials. It detects crystalline materials having crystal domains greater than 3 to 5 nanometers. It is used to characterize bulk crystal structure and chemical phase composition. Okay, so materials can be classified as crystalline materials and amorphous materials. What do you mean by crystalline material? What do you mean by crystalline materials? Materials which have got definite shape, definite structure. They are called crystalline materials. Amorphous materials, okay, they don't have definite crystal structure. Crystalline materials are composed of atoms arranged in a regular ordered pattern in 3 dimensions. We call them as crystalline materials. This periodic arrangement is known as crystal structure. It extends over the distance much larger than interatomic separations. In a single crystal, this order extends through the entire volume of the material. There are 7 crystal systems. You know it already. In PUC, you studied cubic, tetragonal, orthorhombic, rhombohedral, hexagonal, monoclinic, and triclinic. These are 7 crystal systems. What are 7 crystal systems? Cubic, tetragonal, orthorhombic, rhombohedral, hexagonal, monoclinic, and triclinic. So, different crystal structures are based on framework of one of the 14 Bravais lattices. Okay, Bravais lattices. Okay, these are also you studied in PUC level. Okay, and I don't want to go in detail about these things. Okay, so crystalline materials, parallel planes of atoms. Okay, intersecting the unit cell are used to define directions and distances of the crystal. D is spacing, okay, which is defined as the distance between the adjacent planes. The orientation and the interplanar spacing D of these lattices are defined by 3 integers, namely H, K, L. And you know, you have already studied this Miller indices. Reciprocal lattice, okay, Miller indices, we have studied in PUC level. Okay, the HKL designates the crystal face of or family of planes through a crystal lattice. Okay, so what are polycrystalline? We are interested in polycrystalline because we are talking about nanomaterials. Okay, single crystal maybe all the phases, all the sizes are above nanoscale. So polycrystalline means nanoparticles. Okay, materials consist of many small single crystal regions called grains. Grains are separated by grain boundaries, and the grains have, for example, this is a grain. Okay, this is a crystal. There is one more crystal. Okay, these are separated by grain boundaries. Okay, grains have different shapes and sizes, and these are disoriented with respect to each other. Okay? So these are all, they are all called polycrystalline materials. Okay, so it's usually call it as powder. Okay, powder crystals. They're all polycrystalline powder crystals. Okay. So amorphous materials. What are amorphous materials? When atoms are not arranged. When atoms are not arranged in a regular pattern. Okay, regular periodic manner. Okay, the material is called amorphous. They don't have definite structure. Okay, they are randomly oriented. Such materials possess only short range order, that is distance less than nanometer. So these materials are called amorphous materials. They don't show any XRD patterns because only crystalline materials, they show XRD patterns. Okay, they don't show any XRD pattern. Okay, they don't have definite crystal structure. Okay, they are randomly oriented. Okay, there is no periodicity. Okay, so that's the reason they don't show any XRD pattern. What is X-ray diffraction? Okay, I think you already studied, you know, what is interference, what is diffraction, all these things, light. Okay, so this is related to X-rays, diffraction of X-rays. X-ray is a form of electromagnetic radiation. A form of electromagnetic radiation, and having wavelength from 0.01 to zero point 0.7 nanometer. Okay, 0.01 nanometer to 0.7 nanometer, which lies below UV. Okay, UV means above this. Okay, we call it ultraviolet. Vacuum ultraviolet means vacuum means even vacuum can stop absorb the ultraviolet radiation. That's why we call vacuum ultraviolet. Okay. So you require very vacuum systems to absorb the ultraviolet. So air can absorb the light, UV light. So vacuum ultraviolet. Below that we have X-ray. So which is comparable with spacing between lattice planes in the crystal. Spacing between the atoms in metals ranges from zero point 0.3 nanometer, zero point 0.2 to zero point 0.3 nanometers. Okay, when an incident beam of X-rays interacts with target atoms, X-ray photons are scattered in different directions. So scattering is elastic when there is no change in the energy. There is no change in the energy. We call it as elastic scattering between incident photon and the scattered photon. In inelastic scattering, the scattered photon loses energy. Okay, these scattered waves may superimpose, and when the waves are in phase, then they form a constructive interference. And if they are out of phase, they form destructive interference. Okay, constructive interference, you observe some intensity. Destructive interference, you don't see any intensity. Intensity becomes zero there. Atoms in crystal planes from a periodic array of coherent scatters. Diffraction from different planes of atoms produce a diffraction pattern, which contains information about the atomic arrangements within the crystal. There is a Bragg's law, okay, for X-ray diffraction. You have studied this Bragg's law. 2d sin theta is equal to n lambda. What it says? 2d sin theta is equal to n lambda. What is n? It is the order. Okay, n is an integer. Okay, and then lambda is the wavelength of X-ray. Theta is the angle. Okay, and 2d is the spacing. Okay, so Bragg's law is a simple model explaining the conditions required for diffraction. What is Bragg's law? Bragg's law is a simple model which explains the conditions required for diffraction. It is given by n lambda is equal to 2d sin theta. What it tells, okay, right, for all angle theta which satisfies this equation, okay, we call it Bragg's equation, then it forms interference. Okay, so for parallel planes of atoms with spacing DHKL between the planes, constructive interference occurs only when Bragg's law is satisfied. Okay, for example, if theta, it becomes theta plus delta theta. Okay, I'll add some little angle to this. So now you tell me whether it follows Bragg's law or not. No, it doesn't follow Bragg's law. Any angle other than this angle, okay, right, so which satisfies 2d HKL, that is 2d sin theta is equal to n lambda. If this equation is satisfied, then only in constructive interference occurs, otherwise no. Working principle and instrumentation. Okay, we'll discuss how the X-ray diffractometer works. The instrument is called X-ray diffractometer. Okay, the XRD, whatever we use, okay, is X-ray diffractometer. In the diffractometer, an X-ray beam of single wavelength. To get a single wavelength, what we have to do? First, we need one X-ray, right? X-ray beam is required. So the main components of diffractometer are X-ray tube, source of X-ray, you require a cathode which emits X-rays. So usually we use copper as cathode. We can use tungsten as cathode, or we can use molybdenum as cathode. Okay. So we get different wavelengths. For a copper, commonly used cathode is copper. Copper, the wavelength is 0.154 nanometer. What is the wavelength of XRD? If you use copper radiation, copper K alpha, we say K alpha radiation. If you use K alpha radiation, copper K alpha radiation, so we get the wavelength 0.19154 nanometers. That is X-ray tube. In that we use copper cathode, so we generate X-rays. Okay. Right, you bombard electrons or this one, right? So what do you require? Incident beam optics. So to condition the X-ray beam, therefore it hits the, before it hits the sample, you need to condition it. So you need to monochromate. What do you require? So I want only 0.154 nanometer. What I require? You require one filter which allows light of this wavelength, 0.154 nanometer wavelength. So whatever the transmitted light is of this wavelength. Okay. So it may contain so many radiations. It may contain, right, UV, it may contain X-rays, it may contain many things. But when you pass it through this filter, or you can use a monochromator, what do you get? Single wavelength X-ray. Okay, 0.154 nanometer. So you require some optics, beam optics. Okay. I think you studied filters, or you can use, a prism. When white light is passed through this prism, you get what? Different, right? 7 different colors, right? So what I'll do, I want only one particular wavelength. Okay, say this is violet and this is red with GR. Okay, similar to that. Okay, I just want only one color. Okay, I'll use one slit. Okay, I'll collect this blue light only. Okay, so I'm selecting only one particular wavelength. That's why it is called monochromator. Monochromator. Okay, maybe. Okay, monochrome means single color. Okay, so monochromator, we can use a prism in case of visible light, but in XRD we usually use a filter which blocks all the light, okay, and permits only this wavelength light. So we use filters. Okay, so to get the monochromatic light. Okay, so goniometer is another right device that's used here. Goniometer, it's a platform that holds and moves the sample, optics, detector, and tube. And you require a sample holder. Receiving side optics also required. Okay, X-ray beam after it has encountered the sample. Detector to count the number of X-rays scattered by the sample. Okay, so right, the basic components of X-ray, this one are shown in this figure. Okay, you can see this figure. So you require X-ray tube. Okay, optics are not shown. It contains all the optics, right? So condition this X-rays. Okay, and it is making an angle theta with respect to the sample holder. Okay, and 2 theta with the angle to the detector. Okay, 2 theta, right, detector angle. Okay, so it would have gone like this, but it is reflected in this direction. So what is the angle it is making with the detector? It is 2 theta. Okay, so whole setup is fixed in a goniometer. Okay, and here also we use some optics to get the signals. Okay, to collect the scattered X-rays. Okay, the basic components of the X-ray are shown in that figure. Theta is the angle between X-ray source or X-ray tube and the sample. What is the angle? It is making an angle theta with X-rays tube and the sample. And whereas 2 theta is the angle between the incident beam and the detector. Okay, so incident beam is making an angle 2 theta with the detector. We call it as detector angle. Okay, the incident theta is always half of the detector angle theta. Okay, remember this. Incident angle theta is always half of the angle this 2 theta. Okay, this would have gone like this, right? But it is reflected this way. Okay, so this is theta, another theta. Okay, 2 theta, right? So detector angle is 2 theta. Okay, with respect to incident beam of rays, X-rays. The X-ray radiation generated. Okay, so what we do is the basic function of diffractometry is to detect X-ray diffraction from materials to record the diffraction intensity as a function of the diffraction angle 2 theta. Why it is 2 theta? It is detector angle. Okay. X-ray radiation generated by X-ray tube passes through solar slits which collimate the X-ray beam. X-ray beam passing through the slits strike the specimen and X-rays are diffracted by the specimen and form a convergent beam at the receiving slit before they enter the detector. Okay. Right. X-rays are fired here. Okay. They fall on this sample. Okay. And then they are reflected. Okay, with an angle. So this detector angle is 2 theta. Okay. Then we plot a graph of what? Intensity. Okay, what is the intensity we are observing here versus the angle 2 theta. What I'll do, I'll go on changing this angle. Okay, 0 to 90 degree. Okay, this also I need to change. Okay, either I can move the detector and the sample, or I can move X-ray tube and the detector, or I can move X-ray and the sample to get this 2 theta angle. Okay, so intensity versus 2 theta, I'll get some wherever it satisfied Black's law, I get an intensity. Wherever it is not right, following that equation 2d sin theta is equal to n lambda, I'm not getting the intensity. Okay, somewhere I am getting intensity. Okay, from some reflections. Okay, imagine I'll give you some simple example. Okay, imagine a pound of bread. Okay, what you are imagining a pound of bread. What I'll do, I'll cut this bread like this. Okay, along y-axis. So y is z plane. Okay, I'm just cutting this along yz plane. Okay, so otherwise I can cut it like this also. Okay. This is one. Okay, okay, I can cut it like this also. Okay, along x-axis, along y-axis, along z-axis I can cut. Okay, I can cut it like this, or I can cut it this is this is the bread. Okay, I'm cutting it like this. Okay. Imagine, and I may cut this also like this. Okay. Imagine I have drawn like this. I cut like this already, and like this also I cut already. So now I'll cut it like this. Okay. Okay. This I have cut along x-axis. Okay, like this. So what if the angle may this one may be 100 plane. Okay. If the light is reflected from this plane is 100 plane. What should be the second slice? It should be 200. Okay, 200 plane. Third one 300 plane. Okay. Now I have cut along z direction or y direction. The same holds good. Okay. Now I am cutting like this down. Okay. So y direction, right? So it's 0. First slice will be 0 1 0. Second slice will be 0 2 0. Okay, like this. Along z axis, if I am cutting, so it should be 0. First slice will be 0 0 1. Second slice will be 0 0 2. Something like this. Okay. If I cut, okay, sometimes if you go to some bakeries, they cut the slice like this. This is a pound of bread. Okay, sometimes they cut like diagonally. This is what is this plane now? This is 1 1 1 plane. Got it? So right, diffractions may be from different planes, reflections from maybe different planes. Okay, which satisfy the Bragg equation. What is the Bragg equation? 2d sin theta is equal to n lambda. Okay. So working principle and instrumentation of X-ray. The diffracted X-ray beam passes through a monochromatic filter to suppress the wavelengths other than K alpha radiation. Okay, other than 0.154 nanometer in case of copper radiation. So we use copper K alpha radiation, which has got wavelength 1.154 nanometer. Other than that, other radiation should be suppressed. So for that we use filter or monochromator. Okay, diffraction gating can also be used. Okay, but usually we use filters here. The K alpha radiation is generated by bombarding target surface by accelerated electrons. Electron gun you have seen already. How you make electron gun? Anyone? I have discussed this in electron microscope. What we use? Which filament we use to generate electron? Yes?
Tungsten.
Very good. Tungsten or lanthanum boride crystals can be used to generate the electrons. And if we bombard on copper, so X-rays are generated. Okay. So in that there are various X-rays, K alpha, K beta, okay, L alpha, L beta, something like that. Okay. So we take K alpha radiation, which is very intense. So which the wavelength is 0.2154 nanometer. Okay. An instrument can be operated in two ways. Okay, in powder XRD, we use two ways. Okay, one, we can tube is fixed. Usually X-ray tube we don't change sometimes because you are bombarding electron and all those things. So usually X-ray tube is fixed. The sample and the detector rotates to make that angle 2 theta arrangement. Okay, sometimes sample is fixed and you change what? X-ray tube and the detector. Okay, you have seen this. You can either keep this constant, okay, move these two, okay, or keep this constant, okay, move the sample and the detector, so that you can make the two theta angles, okay, and measure the intensities. Okay. Powder diffraction. A single crystal produces only one family of peaks in the diffraction pattern. Polycrystalline, there are so many nanoparticles, so many crystals, and then thousands of crystallites. Therefore, all possible diffraction peaks are observed. So, diffraction is used for the characterization of nanomaterials. What we use? Which kind of XRD we use? Which kind of X-ray diffraction techniques we use? Single crystal or polycrystal? Polycrystalline. For nanotechnology, we use polycrystalline, that is powder diffraction patterns. Okay, so nanoparticles are powders, right? So we use powder diffraction technique, okay, for nanomaterials. So there is an important equation here. Okay, after this I'll stop. Okay, Scherrer equation, Divisional Scherrer equation. What information you get from XRD? You can get the different phases. Okay, which phase it is, with which crystal system it belongs. That is one thing. Another information we get from X-ray is the crystallite size. What is the size of that crystal? So it is given by Divisional Scherrer equation. It's commonly known as Scherrer's formula. Okay. Suppose that a crystal has thickness delta. Crystal has thickness delta measured in a direction perpendicular to a particular set of Bragg planes. Bragg assumed, okay, I'll just show you the Bragg planes 0, 1, 2, 3. Okay, so he assumed that all the atoms are arranged, okay, systematically, orderly, so to form a plane. Okay, so another plane, this is another plane. Okay, so what he said, Bragg, okay, so when the delta is measured, okay, this is delta, the thickness is called delta here. Okay, a D we can say. Okay, you can say delta or so known as D. Okay, if it is small, we call it as delta. Let there be a m plus 1 planes in this set. Okay, imagine there are how many sets? M plus 1. Okay, I just shown only 3. There are m. Okay, here m plus 1 sets. Okay, this is 1 to m and 0 is also there, m plus 1. Okay, define Bragg angle as a variable. Okay, and let theta b be the angle which exactly satisfies Bragg's law. What is satisfying Bragg's law here? The theta b. Okay, this angle is satisfying Bragg's law. So a dash is the ray. Okay, and b right, that theta b is right, is Bragg angle. So you get what you get? Some intensity here when you plot the intensity versus theta angle. So 2 theta angle. So you get some intensity. Okay, in the scattered light. Okay, which is hitting the detector. Okay, right. So what is the equation? N lambda. Okay, usually they are not first order this one. Okay, so n is equal to 1 they have taken. So lambda is equal to 2d sin theta they have taken. It is usually n lambda. Okay, n is any integer. Okay, in this figure, if you see 3.4, they have mentioned ADM make exactly this angle theta b. Okay, the diffraction planes with the theta b with the diffraction planes. Okay, so theta b, this also form theta b, this also form theta b, this also form theta b. Okay, right. So incident rays that makes angle only slightly different from theta b produce incomplete destructive interference. Okay, there will be slightly, it's not completely destructive, not the constructive anyway. Constructive interference, to form constructive interference, you need to satisfy this formula, Bragg's formula. Ray B, for example, makes a slight larger angle than angle theta 1, such that ray L from mth plane below the surface m plus 1 wavelength out of phase B. Okay, so you just see here. Okay, this is making some slightly more angle theta 1. Okay, and theta 2. Okay, they are not exactly they are not following the Bragg's law. Okay, they don't give constructive interference. Okay, neither they do destructive interference. Of course, intensity will be zero. Okay, the intensity of beam diffracted at an angle 2 theta 1 therefore should be 0, because it's right, they are not following the Bragg's law. It is 0 at theta 2 also, 2 theta 2 also. Theta 2 is a right, which m plane below this one, m minus 1 wavelength phase out of C from the surface plane. This defines therefore two limiting angles, 2 theta 1 and 2 theta 2, which diffracted intensity must drop to 0. Okay, okay, only this angle, okay, theta B should give you wavelength, okay, intensity. And what happens to these? Okay, if it is theta 1, it should be 0 here, theta 2, it should be 0. And this is what? This angle is what? 2 theta B. And this angle is what? Slightly, which is here. Okay, what I should write here? 2 theta 1. 2 theta 1. It is making smaller angle, so it should be here. And this should be here, should be this 2 theta 2. Okay, and only I am getting intensity at what? I'll draw it a little bit bigger. Okay, I can show it in the next slide. Okay, so here, this is B, angle B. This is 2 theta B. So where you get intensity maximum here. And 2 theta 2, smaller angle, theta 1, larger angle they have taken. Okay, so intensity becomes 0 there. Okay, they are not following the Bragg's equation. Theta 1 and theta 2, small angles other than the theta B. Okay, which do not follow 2d sin theta is equal to n lambda equation. So the intensity becomes 0 in theta 1 and theta 2 case, whereas theta B is following that Bragg equation, so it gives some intensity. Okay, so this you can see here. Okay, and this width we call it as B. Okay, this width we call half of the maximum. It is distance, approximately distance between theta 1 minus theta 2 it is. Okay, so this is actually intensity should be theta B. Okay, other than theta 1 and this one, okay, they are here. Okay, so 2 theta angle. Okay, this is what you get from this diagram. Okay, so the width of diffraction curve, okay, increases as the thickness of the crystal decreases. Okay, what increases? Diffraction curve increases as crystal size decreases. Okay, for example, a crystal with 20 nanometer. I have another crystal with 40 nanometer. So here 20 nanometer, I'll get broader peak. 2 theta versus intensity I. If I plot this graph, what I'll get, if the size is 20 nanometer, I get this peak. If the size is 40 nanometer, okay, so what happens to this one? Okay, it will be like this. Okay, you get sharper peaks. Okay, as the size increases. Okay, this is for 40 nanometer crystal, and this is for 20 nanometer crystal. Is that clear to you? 20 nanometer crystal, smaller size, gives broader peak. This peak will be broader. Okay, if the size is crystal size is smaller. Okay, what do you get? You get broader peak. Okay, if you get right, larger value of crystal size, you get, what do you get? Sharper peaks. Is that clear to you? So B value decreases with increase in crystal size. Okay. So because angular range 2 theta 1 minus 2 increases as m decreases. Okay. The width B is usually measured in radians. Okay. What is the unit? I'm not using degree here. I'm using radians. At an intensity equal to half of the maximum intensity. What we call it as full width at half maximum. Full width from here to here at half maximum, half of the intensity. This is 100. Okay, arbitrary units. So if I measure it at 50 arbitrary units, so it is half of the maximum. So whatever the full width, that is called B. Okay. So B is equal to half of the 2 theta 1 minus 2 theta 2. So I can say theta 1 minus theta 2. Okay. So path difference. Okay, path difference equations for these two angles are similar but related to the entire thickness of the crystal rather than the distance between the adjacent planes. So 2d sine theta is equal to m plus 1 lambda. 2d sine theta 2 is equal to, I have defined these two. Okay, m plus 1 plane and m minus 1 plane I am taking. So theta 1 and theta 2, m plus 1 and m minus 1. So by subtraction, what you can do. So this minus this. Okay. So m cancels. Okay. So 1 minus 1 it becomes plus 2. Okay. 2 cancels out here. Okay. What you get is delta sin theta 1 minus sin theta 2 is equal to lambda. Okay. So sin theta 1 minus sin theta 2, mathematics, you can write, what you can write, 2d cos theta 1 plus theta 2 by 2 and sin theta 1 minus theta 2 by 2, and lambda I am keeping it as it is. Property of sines and cosines. Okay. Right. But theta 1 and theta 2 are very near. Okay. Whatever I am talking about, they are very near to B only. Very small angle difference. Okay. So they are lying here. Okay, at the edge of this curve. Okay. So this is the mean. Okay, this is which is following Bragg equation. These two are not following, but they are just close to that Bragg angle. So right. So they are very near angles. Okay. So what I can do, right? This equation I can simplify. Right. So what I can do is theta 1 plus theta 2. I can take it as 2 theta b. Okay, directly. Okay, theta 1 plus theta 2, I can take it as 2 theta b. Okay. So theta 1, this, what happens to this equation? Theta 1, sine of theta 1 minus theta 2 by 2 is theta 1 minus theta 2 by 2, approximation. I am just taking some approximations. Okay. So in this equation, I am just taking this approximation. Okay. So this theta 1, sine of theta 1 minus theta 2 divided by 2 is equal to theta 1 minus theta 2 by 2. This is approximation. Okay, for small angle theta. So what I have, 2d cos theta 1 plus theta 2, I can say theta. Okay, theta, what happens, this becomes 2 into d, that is delta, into cos theta 1 plus theta by 2, that is 2 theta b by 2, that is theta b only. Right? is equal to lambda. Right? So you can write, okay, 2d theta 1 minus theta 2 by 2, okay, is cos theta b into lambda. Okay, so this is same. Okay, right, sorry, I have to write not lambda, theta 1 minus theta 2 by b. Okay, because this is approximation I am taking. Okay, it's not lambda, it is theta 1 minus theta 2 by b. Okay, so that's equal to lambda. Okay, I had to substitute that sin theta value also, right? So I have forgot on that. Okay, so this into this is lambda. Okay, just ignore this. Is equal to, just ignore this. Okay, just substitute this here. Okay, so what do you get? 2d cos theta 1 plus theta 2 by that is cos theta. Okay, theta b. Okay, theta b into this is lambda. So delta is nothing but this two you can cancel. Okay, so what do you get? Lambda divided by beta cos theta. But more exactly, you need to take the shape factor. That is, you need to take, that is 0.9 usually we get. 0.9 into, that's an approximation. Okay, we get 0.9 into lambda divided by beta cos theta. Okay, b is, we say usually beta. Okay, so this size, right, size of the nanostructure, crystallite size of the nanostructure is given by d is equal to, instead of delta you can take d 0.9 into lambda. Okay, we call this 0.9 as k. Okay, k may have values 0.9 to 9.95 by beta, okay, cos theta. Okay, so d cos theta is beta cos theta. Okay, doesn't matter. This is the equation we use to calculate the crystal structures, right, size of the crystallite. Okay, this is well-known equation. This is known as Scherrer equation. We will solve one or two numericals on this equation. Okay, what do you do? Just go through this derivation. You will understand. Okay, if you just go through, I mean, just follow this. Whatever I am discussing today, just go through this video and also try to practice this. Okay, usually this this Scherrer equation is usually asked in the examination. Okay, and also numericals on Scherrer equation will also be asked. It's also known as Debye-Scherrer equation. Okay, Debye modified this equation. That's why it's called Debye-Scherrer equation. Okay, k lambda by beta cos theta. Okay, what is this equation? D is equal to what? K into lambda divided by beta cos theta. What's right now? Half detector angle. Okay, full detector angle is 2 theta. Okay, half detector angle is